Hello and welcome to the second lecture on computer graphics. This lecture will be dealing with mathematics, which is necessary for various tasks in computer graphics. It will be a mix of various topics, which you will find beneficial along the way of the course, and you will be able then to successfully apply them to solve a particular problem, often of a geometric nature. Let's begin with certain notational definitions. So we will be dealing often with functions, and these functions or mappings, they will be defined from a certain space, if you like, to another space. Like, for example, here a function f is defined from the R to Z, which means from the domain of the real numbers to the codomain of integer numbers. We will call the space in which the input values are located the domain, and the outcome of the function with these input values will be resulting into a so-called codomain, but here also in the book called target. So if we are having an point A within our domain, its image after applying this mapping is the function of A, and this is called its image. If we take all A's or all points or elements of the domain and we map it to the codomain, we will create a set which we will define as a range of a function. Now, if we have a mapping from the domain to the codomain, we can also invert this mapping and map from the codomain into the domain, and we will call such a function an inverse function, and we will denote it by the capitalized -1 term. In order for an inverse function to exist, we would need to have certain properties of our function f to be fulfilled. So, for example, our function or f from A to B would need to be bijective, and the bijective means that we will have the bijective mapping means that the mapping is or function is injective, and at the same time it is surjective, which are two other properties which need to be fulfilled for a function or mapping to be bijective. So what is injective? Injective means that every element in the codomain, in the domain, will be mapped to a unique element in the codomain or target, which also means that every element in the codomain will have at most just one element to which it is mapped from the domain. On the other hand, the surjective mapping means that for every element in the target in the codomain, there is a element in the domain, which means that there is no element in the target which will not be mappable to the domain. And if these two conditions are fulfilled, then we have one-to-one mapping between elements in the domain and the target, and therefore this mapping can be inverted. If we would not have the bijective condition fulfilled, then we will not be able to map the elements from the codomain back into the domain with the inverse function, because such a function will not be well defined. So for example, the function f(x) equals x powered by 3 is a bijective function, because we can assign to every fx a unique x value. But for example, the fx equal x squared is not a bijective function, because we know that, for example, -2 would result in x equals -2 will result into fx equals 4, and the same will hold for the x equals 2, which will again result into 4. So one element in the codomain, in the target 4, will have two so-called pre-images, values from the domain to which it maps, which violates the bijective condition. Now, let's have a short recap on the very often and necessary element of computer graphics and geometry in general, which are angles. We will be dealing with angles for computing various relations of our geometric elements in the scene and the camera and the light interactions, and therefore we need to understand their basal properties. So angle is really is actually can be defined as a length on a unit circle. So imagine a unit circle is a circle, which I will just draw here on this existing drawing already. It's a circle which has a radius of a length 1. So I will draw it here, r equals 1. And this is a unit circle, and the angle, let's say the angle phi, which we have here, the phi is equal to the length of this arc here. So we know in radians. So of course we can define the angle in degrees, and then this length is no longer preserved. But if we are talking in radians, then this will hold on the unit circle. So if we have a phi, which will be, for example, pi half, then the length of this segment will be pi half indeed. We typically define the range of the angles to be between pi or minus pi and pi. So we typically start on the right hand side with the 0 angle, and this way the angles counterclockwise are increasing, whereas here on the other side this will be the value of an angle pi. If we will go the other direction, this will be the minus direction. This angle, the same angle, can be defined also as minus pi, because this is the length, but in the negative in the clockwise direction. So if we define the range of angles from minus pi to pi, we are really defining, really the entire circle of an entire length of 2 pi. Now, the angles come handy in various contexts, like, for example, in the context of dealing with triangles, or with dealing of various relations of various lengths. So, let's start with the Pythagorean theorem. The Pythagorean theorem, as we know it, is defined as, and I will write it here with small, that a squared plus b squared equals c squared, and this holds in the right angle triangle. So one of the angles in our triangle is the right angle, which means that it is of a value pi half. And the other angles we do not necessarily know, but the A would be here this one side, B would be here this another side, and C would be this so-called hypotenuse. Here I am having a slightly different notation where I'm having a squared plus o squared equals h squared, which means that adjacent side plus opposite side equals squared, both, equals hypotenuse squared. So how can we come up with this conclusion? How can we prove it graphically? So let's have a look at the image on the right hand side where we have something, various graphical elements, and we have one side of a big rectangle, and one side of that is a plus o. This side a plus o squared, this is a term which we have here, a plus o squared. This is actually the area corresponding to this entire square here. And now we are saying that a squared plus o squared equals h squared. And h squared is just this hypotenuse here. This is the h, this is the h squared. Okay, so now how do we end up with this relationship? So let's have a look at what is a plus o squared. Allow me to write it this here on the top. A plus o squared equals a squared plus o squared plus 2ao, right? So we have here this, this term 2ao, and what does it mean? So AO, let's have a look at the drawing. Here we have, for example, one of the A's. Here we have O's. A times O would be such a rectangle. If we divide it by half, then we will have the area of one of these triangles. So AO half will be one triangle. AO will be area of two triangles. As we can see, we have here 1, 2, 3, 4 triangles. So this is in total 2AO. So now we can see that if we look at the areas, the AO squared minus 2AO is, so minus 4 of these triangles is indeed equal to h squared, and a plus o squared minus 2ao is so a plus o squared minus 2ao is equal to a squared plus o squared, which proves that this is equal to h squared. Hopefully you were able to follow me. Now let's have a look at the angles. We are defining various so-called trigonometric functions where we are expressing some function with the parameter with the parameter of an angle, where these different functions are defined on a right angle triangle. So let's define that our phi is an angle which is defined here. And its function sine phi, it's so this is the h, and the opposite side to the angle is this one, and the adjacent side to the angle is here. So sine phi is the ratio between the length of the opposite side and the hypotenuse, and cosine phi is the ratio between the adjacent side and the length of the hypotenuse. And for example, tangents function of phi is the ratio between the opposite side and the adjacent side. Sometimes we deal with our representation, our geometric representation, in different spaces than in Cartesian spaces or Cartesian coordinates. Cartesian coordinates are defining us in Cartesian space, Cartesian grid, the distances along each coordinate axis. And by this we can define, for example, here, that the point A, which we can see here, will be in Cartesian coordinates having value 1 for the x, and for the y dimension it will be something less than 2, so let's say 1.9. And however, this is not the only way how we can define this position of the point A in this space. We can also define it in so-called polar coordinates, and those are not defined by the x and y coordinates, but by a radius of a certain radius and a certain angle. So we are defining in our coordinate origin a point from which we are measuring a radius of an imaginary circle, and this radius, so the length, the distance between the origin and the point A, is the one parameter, and the other parameter is the angle phi, which is spanned between the horizontal axis and the vector between the origin and the point A. So this is just another way how we can define the coordinates between of a point in Cartesian or in polar coordinates. There could be more. Sometimes we are interested in transforming coordinates from one coordinate system to another coordinate system, between Cartesian coordinates to the polar coordinates. So, for example, the Cartesian coordinates, if we have them defined, how do we define the polar coordinates? So we need to find the value r, and if we have the values x and y, but here, let's call it x and y here in this drawing, then the r can be simply computed as we just had it. R squared is equal to x squared plus y squared. So r is equal to square root of x squared plus y squared. And this is obvious and trivial. How can we compute the angle? The angle can be computed in the following way. First, we can compute the tangents, tan of the phi, remember, is equal to the opposite side, so this would be the y, divided by the adjacent side. So this will be the x, or if you like, the s and the c, as it is depicted in this drawing. And then we will perform the operation arc tangents, and we will get from the tangents y the value of phi. We have also another very practical function, which is called the L02 function, which transforms us from, so phi equals L02 of S and C. So of one of the opposite length of the opposite side of this triangle versus the adjacent side, whether it is called S and C or Y and X. Doesn't really matter. Let's have a short recap on vectors. Vectors are geometrically defined by a direction or a length, and they really are offsets. So vector is not a somehow existing in space at a particular location, but it is an offset and can be applied to any points or other geometric elements to transform them to another position. So, and this offset can be, for example, defining point locations, because this offset can define the location as an offset from the origin. There are several operations which we can apply to vectors. Like, for example, we can express a vector by other vectors. Like, for example, here on the right-hand side, we can see that we can express an vector a plus b as a vector a and summed together with the vector b. How does it look geometrically? We take the vector a and at the end and place it somewhere, so to say, and at the end of its offset, we place the vector b. And then if we connect the beginning of the vector a with the end of the vector b, we will obtain the vector a plus b as the result. So this is how the sum of two vectors is defined. We can also define a negative vector to a particular vector, like, for example, a vector minus a as a negative vector to the vector a. And such a vector will be exactly the same, having exactly the same orientation, and also it will have the same length, but it will be pointing to a different direction. So, for example, a plus minus a would be equal to 0. We can use this for expressing a subtraction among vectors, because we can simply use the vector minus a as a sum to a vector b, for example, as it is shown on the image below. So here we can see the vector b and the vector a. So the vector minus a will be this one, and that's why we are getting the vector b minus a, which is the b plus minus a vector. So this is how we can define the subtraction. We said that we are defining vectors and they have their own length. Often we are interested in the so-called unit vectors, which means that these vectors are of length 1 and they do not then need to be normalized and do not scale our properties within the graphics algorithms. Vectors are great for defining coordinate spaces. If we have vectors in a certain dimensional space, we can talk about some linear independence of vectors. What is a linear independence of vectors? It means that a vector can be okay, or for linearly independent, that a vector cannot be expressed as a linear combination of other vectors. So for example, in 2 dimensions, if we have 2 vectors defined which are not parallel to each other, these 2 vectors in 2-dimensional space can be used to define any other vector in this 2-dimensional space. Here the graphics helps the intuition or the recap of what we already know. Look at the vectors A and B. They are quite wildly defined. They are not equally sized, and they are not nicely perpendicular to each other. And yet, we can, with these 2 vectors, express the vector C. Just look how it can be achieved. If the vector C can be expressed as a sum of the 2 times the length of vector A plus half of the vector B, and we will obtain the vector C. Often it is very practical not to have wildly defined vectors, but for Cartesian coordinates, for example, we are using vectors which are forming orthonormal bases. So for 2 dimensions, it will be 2 vectors which are perpendicular to each other, and at the same time, length of both of these vectors is equal to 1. So here we have an orthonormal basis vectors x and y, and they are perpendicular to each other, as we can see, and also they have the same length. And in this space, we are defining other vectors through these 2 vectors, really. And when we are talking about, for example, vector A and having coordinates, so vector A is having coordinates xa and ya, we really mean by that this description. So it's a multiplier of the vector x, which is the basis vector, and another summed with another vector which has a multiplier ya. And through this, we can obtain the vector A. Like, for example, here we have the vector, not the vector A, but the vector C, and this vector C we can obtain by 2 times x plus 0.5 times y vector. This is super practical. We already have discussed that these vectors need to be orthonormal to span a practical coordinate system. And we can perform a normalization of a vector by dividing the vector by its length, and then by that achieve the length 1. So how do we define the length? We have already mentioned that it is a square root of the sum of its components. Here we have it for the 2-dimensional vector, but this can also hold for 3-dimensional vector or vectors of more dimensions as well. Then we have various operations, various multiplications among vectors defined, such as, for example, the inner product or the dot product, which is defined as the magnitude of the 2 vectors, their multiplication, times the cosine of the angle which is spanned between these 2 vectors. Here you can see it here on these graphics. So this is the definition. Please note that it also equals to the sum of the coordinate terms multiplications, as we will show in the next slide. The dot product can be also practical for performing projections of one vector onto another vector. So a projection means that we are projecting a vector onto the other vector, as shown in this graphic here. And what does it mean? Well, we are basically, what we want to achieve in this projection will be to know what is the length of the projected vector A onto vector B. How do we find it out? For that, we can have a look back to the dot product, and we can, or actually we can see from the Pythagorean theorem, or actually from the right angle and the functions, that what is a cosine phi? Cosine phi was defined as adjacent side, or length of the adjacent side, to the hypotenuse. Now the hypotenuse in this case, unfortunately for the naming convention, is equal, so I will put this just into some kind of a memory, is equal in our case to A projected on B divided by A, because A is here the hypotenuse and this is the adjacent side, really. So adjacent side divided by the hypotenuse. And if we are now, or actually the length of this, and therefore this projection, the length of the projection, is equal to the length of this A projected onto B is equal to A times cosine phi, because we put the length of the A onto the other side. Now, we can also express it by the dot product, because the dot product is the cosine phi is equal to the dot product A times B divided by magnitude of the vector B and multiplied by the vector A. So as we have already here the magnitude of the vector A, we can just simply say that this equals to A dot B's dot product divided by the magnitude of B, because the A here has been cancelled out in the denominator by the A standing outside the cosine phi. Let's have a look at defining the how did we end up with the dot product being the multiplication of the coordinates summed up together, meaning that why is it so that A times B, or dot product between A and B, equals AX BX plus AY times BY. So we can observe that A is really AX, a multiplicator for the x coordinate axis, plus AY multiplicator for the y coordinates, and for the multiplier of the vector y, which is perpendicular to the vector x, multiplied by the same for the vector b. So bx plus by. And now let's multiply this out, and we will end up in ax bx multiplied by x and x plus, and now before we go any further, we can see that this is a dot product between with itself, and the dot product with itself is equal to, so what is x times x dot product with itself is equal to x magnitude times x magnitude times cosine phi, which is 0. Cosine of 0 is 1. This magnitude is also 1, 1. So it's 1, 1, 1, 1. So x dot product with itself is equal to 1. And dot product with y, so x dot product with y equals, again, magnitude of x times magnitude of y times cosine phi between x and y. And this is 90 degrees. So cosine of 90 degrees is 0. So dot product between x and y is 0. Therefore, this term, mixed term between ax and by will be 0. And also between ay and bx will be 0 because of the dot product, because between y and x or x and y is 0. And we will end up only with ay by. Again, let's say dot product, which in turn ends up being 1. So this is why we have the dot product between a and b equaling the multiplication of its coordinates summed up together. Dot product is not the only operation or product operation on vectors. We also, for example, know the so-called cross product, and the cross product is not coming up as the outcome of the cross product is not a scalar value, but the outcome of the cross product is actually another vector. And here we can see it graphically. We have again vector A, we have vector B, and the cross product of the vector A and B is another vector, so with 2 or with 3 coordinates. So the cross product exists in 3D space, and this cross product is giving us another vector which is perpendicular to both A and B, even if these two are not perpendicular to each other, and its length is equal, the magnitude of its length is equal to the area spanned by the A and B. And the cross product as a magnitude of it is defined as magnitude of A times magnitude of B times sine phi. So the sine of the angle between these two vectors. So now let's have a look what it means. If we have A and B here, then it basically gives us this defines us this area, is what I was talking about, where A is this length and B times sine phi. So let's do B here and sine phi. So let's say that this is the phi here between A and B, and the opposite, this is the opposite side to the phi, and this is the hypotenuse. So sine phi here is defining us the ratio between the opposite side and the hypotenuse here. But the hypotenuse at the same time is B. So it really gives us the value, this term here gives us the value of this of this of, of this length, and here this would be perpendicular to the A. So it basically gives us an area of this type of rectangle, which we know that if we are just moving this point, we are not changing, we would, and both of the points, so we are moving this point and this point by this amount and this amount, which is the same, we will create a parallelogram which would have the same area. So this area is the magnitude of the vector of the cross product. Now, how is this cross product computed? We have now vectors A and B, and these vectors A and B here are defined as XA, YA, ZA, and vector B is defined as XB, YB, and ZB. And the cross product is defined for the x-coordinate of this cross product vector is the multiplications of the YA times the ZB minus ZA times YB. And I don't know how you remember this, but I just use a mnemonic help where I first write 3 to 1, 3 to 1, and then I flip each pair of the numbers. So 3, 2, I flip to 3 to 3, and 1, 3 to 3, 1, and 2, 1 to 1, 2. And then I have these three coordinates where the second coordinate times the third coordinate of the other vector minus, here is always the minus third coordinate of the vector, of the first vector, times the second coordinate of the second vector. And this holds here and in all of these cases. So this will be the x, this will be the description for y, and this will be the description for z. Now, as opposed to the the scalar product, the cross product is not commutative. So we will get a different result if we do cross product of A with B and with B and A. The vector in itself will be more or less the same, and it will have the same magnitude. It will have just be pointing to a different direction. And it is equal to, so B, cross product B and A is equal to cross product minus A, cross product with B. Similarly to explaining you how we came up with the dot product, I will explain you how we can define this cross product, for which I'm using the mnemonic help, but we can also derive it from the following based on the definition which we started up with for the dot product, for the cross product. So A cross product with B is really, what is it? It's XA X plus YA Y plus ZA Z cross product with X B X plus Y B Y plus Z B Z. Okay? And here, again, let's try to multiply it out, and we will have that XA, XB will result into X cross product with itself, for example. And now let's have a look what is a cross product. It is the magnitude of it cross product with itself is equal to X times X magnitude times sine phi. Whatever the X magnitude is, which would be 1 in our basis vector, but the sine phi, sine of 0 angle, is 0. So this is equal to 0. Therefore, this whole term will be 0, and this whole term will be 0 as well. So we will only have the mixtures of the vectors which are not cross product with itself. So we can have a look at what it means. So the XAX is this term is gone, but plus we can continue XAX XAYB X cross product with Y, and X cross product with Y, what is it? It's not 0 in this case, it's not a 0 vector, but it is a vector which is perpendicular on these two. And actually, in fact, it is the vector Z. So this is a vector Z. Plus, so we continue, XAX, XAX, or sorry, again, Z, B, and X dot product with Z. What is the Z dot product with Z? The X dot product with Z. It turns out to be minus Y. Okay? This is where the minuses are coming into our equation. So we have now performed some of these multiplications, and we continue with this term now. So YA XB Y cross product with X. Y cross product with X is minus Z. And then the cross product with Y will be 0, so that the cross product between these two terms, the second terms, will be 0. And then we will have plus YA ZB Y vector cross product with Z vector. And finally, ZA XB will be Z cross product with X. What is Z cross product with X? It actually is Y vector, positive, and plus ZA YB Z cross product with Y, and z cross product with y is actually minus x. So now, if we collect these things together, we will have the following result. Let's have a look for which are the factors which are corresponding to the basis vector x. That is, in the first one, we have y times z, here I'm sorry, is x. So zya, zb is minus za yb is are the values for the x coordinate of our new vector, plus za xb minus, so this is here, ya, oh, but this, oh, sorry, minus y. Where is minus y? This is minus y. xa zb is for the y coordinate, plus x a y b minus y a x b is the multiplier with the z coordinate of our new vector created by the cross product. So this is how the cross product can be derived if you don't have the mnemonic help as I do with this 3-2-1, 3-2-1 trick. We have, by our vectors and vectors which are nicely defined like x, y, z coordinates in three-dimensional space, we can create so-called coordinate systems. And these coordinate systems are defined by the offset vectors in each coordinate dimension and also by a certain origin. We can define the origin as O or as 0. And typically, if we write a vector v equals 2, 3, 1, what we mean by that is 2 times x coordinate plus 3 times y coordinate plus z coordinate of the z vector. But we often abbreviate it just to the multipliers because the vectors are somehow part of the coordinate system. If we are talking about points, we can define the points similarly as 2, 3, 1. And this will mean that we are performing an offset from the origin. So this is really equal to O plus V, which brings us from the origin position through the offset vector V to the point P. So we can see it here also described that where we have one of our vectors is u, which is defined in the by the multipliers of our basis vectors x, y, z. Now, let's An interesting point is that we do not need to have just only one coordinate system, but we can have also a so-called local coordinate system, which can be defined by the basis vectors, which are somehow defined also in the global coordinate system. So, for example, if you look at this drawing, we have here our global coordinate system defined by the XYZ axis and the origin, and then within this global coordinate system, of the world in graphics of the scene, we will have local coordinate system of individual objects, like for example, of this plane. And for this plane, we will have the direction of view, for example, defined by the vector u, and we would like to define a coordinate system for this plane itself, so that we can define offsets with respect to this coordinate system. So here we will also have three orthogonal vectors, u, v, and w, and we will have the center of the coordinate system, which will be the point P. And as I told you, the point P is defined in the global coordinates as this offset from the origin of the global coordinate system. And we will, however, often write it just as the point P with the coordinates x, p, y, p, c, p. Now, it is important in many cases to be able to transform the values between these two coordinate systems. So if we have, for example, an point A defined here in the UVW coordinate system, in the local coordinate system, we can also express it by the global coordinates by simply putting into its definition the definition for the u, v, and w. So here will be the coordinate systems for u, v, w, which will be x, v, x plus y, v, y plus z, v, z, and similarly x, w, x plus y, w, y plus z, w, z. And these vectors we can simply put instead of these values here, and through this we will define the global coordinate system for the point A. So the point A will be located somewhere, and it could be defined by the global coordinate system or the local coordinate system UVW. Similarly, we can also define a point which is defined in the global coordinate system, like the point B here, in the UVW frame. And how is this done? This can be done by getting the individual values of UB, VB, and WB, these multipliers, by a scalar product of the vector U with vector B and the vector V with vector B and with vector W with the vector B. Let's have a look what is meant by this. So imagine that the vector B we will have in the UVW coordinates, and this will be BU times U plus BV times V, or time, and plus BW multiplier of the vector W. Now, if I will do so this is my vector B in the UVW coordinate system. If I now do a dot product of the U vector times b, it equals to u times b u times u plus bv times v plus bw times w. We know that the dot product with itself equals to 1, and the dot product with a perpendicular vector, like v or w, with the u will equal to 0. So this means that u times b is really just bu. I'm calling it here the bu. Here it is called the ub, but by this is meant the same thing. Often, we will have some vectors a and b in graphics, and we would like to define a coordinate system based on these two vectors. Now, this might be a little bit easy if these two vectors are already orthonormal to each other, so they are of unit length and they are perpendicular to each other. So the job is easy. We will just do, in such a case, we will just do the cross product A with B in order to create the vector C, which will be also already orthonormal, and it will be create an orthonormal frame. In case these two vectors are not nicely unit vectors, as I did just described, and are not orthogonal to each other, so these two vectors are simply just vectors like this. This would be the A and B. We can create a UVW frame in the following way. First, we normalize A. So we divide it by its magnitude. Let's say this A, this is the normalized A. So this is A divided by the magnitude of A, and this is equal, its length is equal to 1. Now, here comes the trick. So this will be, now we will call it W. This is W. And the W, now we will make the cross product with B, or B cross product with W. And by that, we will create the vector U. W is already normalized, but B isn't. Doesn't matter, we can normalize it afterwards, and then we will have also U as being normalized. So this vector and this vector, the cross product between those two will be a vector which is pointing into the screen, into the whiteboard, into the slide. And it is of length 1. So now we have the vector W, we have the vector which is pointing orthogonal to W and B. And now the third vector which we need to calculate will be the vector V, which we again can calculate as the cross product between W and U. These two are already normalized, so we do not need to perform additional normalization. So the vector V will likely be pointing this direction, so it is orthogonal to W, and it is also orthogonal to U, which is pointing into the slide. Let's start a discussion on curves and surfaces. We can define curves in various forms, for example, in parametric form, but also in a very practical form, which is called an implicit form. We probably remember how we can define a circle. Circle can be defined as by an implicit equation by points which are at a certain distance from a from an origin. The origin here will be defined by the xc and yc values, so that's the center of the circle. And if the distances, if the squared distances of this of this if the square distance is equal to a certain radius r, then it satisfies for that point xy to be on the circle. So if it's of a if it's r squared minus r squared will be equal to 0. For everything, every point which is inside this circle, it will be a value which is smaller than 0. It will be a negative value because smaller distance from the xc, than r will result in a negative value. And consequently, if we will have a point xy somewhere outside this circle, the functional value will be positive. We can also describe it in a vector form where we are having 2 points point on the possibly on the circle or inside or outside minus the center. This is a squared minus r squared is equal to 0. So this is equivalent, and if we sort of square root this description, we can have a representation of the same equation where the magnitude of the vector p minus c must, if it's this, equal to r, then the point P is on the circle. We can see here that our point, our function, our circle here equals to 0 if the points belong to this circle for the point, for this particular equation of the circle. For the point in the center, which is 0, 0, we will have the functional value of -1. This will be the smallest value which we can achieve. But for points which are outside, we can create, oh sorry, so this is 1. This is 1. This is minus 0.5, this value, this smaller circle. And the larger circles are then having the functional value larger than 0, and it will be 1 here, 1.25 or 3. So, and this implicit representation, as we can see, is not only defining us a circle, but is also defining us whether a particular point is inside or outside the circle, or even how far it is from the circle. And for the often we are defining for our representations, for our functions, gradients, which are very practical for example, defining normal vectors, which could be used in various contexts, like, for example, in evaluation of illumination. These gradients are essentially defining us the direction of a maximum slope of the function. So if I have a certain values x, y at a particular position, if I am now moving from this xy position, in which direction will be the functional value the highest? Here on this drawing, you can see a line. So this is an implicit line equation here, where the fxy is equal to 0. If we will have other points, so these points, if you can imagine, that are lying in the xy plane, and if we have now a point which is lying out above the xy plane, like for example, no, if we have a point which is not lying on this line, but this lies outside this line, it can have a non-zero value for this implicit equation formulation. And it can have positive or negative values. So for the point AB, we will have actually a positive value because we can see that this direction goes, the function becomes higher. So this is the functional value of the FAB, and it will be a positive high value. So from the line, the gradient will be the point, the direction in which the x and y should be changing in order to achieve the highest functional value. So it turns out that this maximal direction of increasing the functional value will be orthogonal to our line, which is the implicit line defined by fxy equals to 0. Now, it can be, we know that the gradient can be expressed by partial derivatives of a function. A partial derivative expresses how much a function, a two-dimensional function, changes when one of these dimensions is kept constant and the other one is infinitesimally changing. Like, for example, here in this drawing, we can see how much is the partial derivative value if we are changing x dx, how much is the f changing. So this is the partial derivative. Now this discussion leads to the interesting or known fact that the gradient is defined by the partial derivatives. So imagine now we don't know that, but what we know is that if we have a vector which is the vector A, and it will be here called vector A with the coordinates xa and ya, or it will be called here also, these coordinates will be called also delta x and delta y as it is in book, because this vector A here is defined by the coordinates delta x and delta y. So if we are having such a vector and the gradient to it, which is orthogonal, which means if it's orthogonal, its dot product has to be 0. So this means although the values xa, ya, and or the vector, none of these two vectors is a 0 vector. So, and if we look at the partial derivatives along the x, along the a, vector, we will realize that the partial derivatives along this line are also 0, because along this line the function doesn't change. It equals to 0. So we can see that the partial derivatives are actually can be expressed. So this is also a dot product here, which we can, as we see. So this dot product, it means that the xy, and so if we have a dot product of two if we have a vector v, and this vector is having vx and vy as coordinates in 2 dimensions, in order to construct a vector which is perpendicular to it, so let's call it w, the w can be in the simplest way defined as minus vy vx. So we switch the coordinates and one of them gets a negative value. So this means that in order to construct to have a zero value, which is the functional partial derivative change along the line, we have for the dot product, the xa and ya have to be somehow equal to k times, and now the partial derivative of according to y minus partial derivative of x, because we have switched these two coordinates and the x got a minus. But now the x, this also implies that the gradient coordinates of x and y coordinates need to be somehow also, as they are perpendicular, this means that they are k prime times the partial derivative in one dimension and partial derivative in another dimension. And from this, the consequence leads that as this k can be any positive value, let's take the value 1, the gradient of the function is defined by its partial derivatives. In computer graphics, we will be often dealing with lines. These lines are, for example, used in defining rays, which will be traced from the eye point into the scene in order to be synthesizing the image, as we will see on the next lecture. The definition how we often define line is defined through the so-called slope-intercept form, which defines the y-coordinate value through some linear function involving the x-coordinate. It has the m value, which is the slope, which really is a tangents of the angle which we have here. So this is y, this is phi, and tangents phi is equal to m. And then the y-intercept value, which is b, which this value is performing an offset of when x is 0, how much, what is the point through which the line intersects the y-axis. So it shifts the line up and down depending on the b. But this is not the only form how we can define a line, and we can, by putting all the terms onto the left-hand side, we can again create an implicit form of a line. Here, such an implicit form will have again an additional benefit, that we do not necessarily need to express it as a if it's equal to 0, it will be, points will be on the line. But if our function value of this implicit function will not be equal 0, but some other value, it will define us that the point at a certain distance from this function. If we will have 2 points defining a line, such as point 0 and 1, defined by the coordinates x0, y0, and x1, y1, then we can construct an implicit form of such function by defining an an implicit form of the function through the implicit form where with the terms a, b, and c. Such implicit form will mean that if we will enter a point x0 into such equation, it will be equal to 0. And so it will be the case if we will enter the point 1 into the equation with the coordinates x1, y1, and also all the points in between, which are spanning the vector 0, 1 between these 2 points. What we do not know is these points A, B, and C, and we would need to calculate them. However, what we know is that if we would calculate the gradient of this function, it will end up from the partial derivatives, our gradient of our line, let's call it L, L is defined by these 2 points, is a vector which is A and B. Partial derivative according to x will result into A, partial derivative according to y will result into B. So we know that the A and B is a normal vector, perpendicular vector to our line, defined by these 2 points. So how can we define the A and B? Can be from the fact that we know that the vector between vector L, let's define the vector L between points x1, x0, y0, and x1, y1 is equals to Lx and Ly, and that equals to x1 minus x0 and y1 minus y0. Now, if we have a vector which is perpendicular to the vector L, we can simply, so such a vector will be simply, could be as y0 minus y1. So we put this coordinate into the other coordinate and negated it, and the other coordinate will be x1 minus x0. And this is what we did here. So you can see here that this is A, as we described it, and this is now the B part. The only thing we do not know is the point C. What is the value of the C? That's what we do not know. However, we can express it. So now we know what is A and B, and now we will compute the C part. The C part can be calculated by simply entering one of our points into the equation, which should be equal to 0. So let's do it. So y0 minus y1 times, let's say, x0 plus, it could be the other point as well, x1 minus x0, y0 plus c equals 0. Now, y0 x0 minus y1 x0 plus x1 y0 minus x0 y0 plus c equals 0. Now we can observe that we have the same term twice here, and this is this term, because the multiplication is of course commutative between scalars. So we will end up into C equals, and this is a negative term, so now on the other side it will be positive, y1 x0 minus x1 y0. And this is exactly what we have here just by switching these two. The beauty of the implicit form is that we do not only define the line, but also an entire plane, if you like, with the distances from this line. So, for example, we can define a point P at a particular distance to the line by defining a point on the line which is a projection of the point P onto the line, plus the vector which is perpendicular to the line vector. We don't know how long this vector is and which direction it goes, but we know that it's a perpendicular one as it is a projection. Therefore, it is defined through the A and B terms. However, there is an unknown k. So the distance between the point P from the line is this vector, which is also equal to Ka, Kb vector. If we take these two, the distance of the vector is defined as k squared a squared plus k squared b squared and square root of that, and we can take out the k out of each term, so it will be k squared times a squared plus b squared, and the k can be even further taken out from the square root, and then we will end up in this term for the distance. However, we can define the distance directly from the functional value of that point. Remember, the point xp yp is equal to some point x and some point y, which we do not really, some coordinates x and y, which is the projection of this point on the line, and plus some offsets from which is the vector defined, which is perpendicular to our line. And if we look at these values, so if this is our function, we can put this point into our function and define what is its value. This value is here, but let me show this to you once again. So, so this is xp, this is yp, and if we put it into the equation, then we have a times x plus k a plus b y plus kb and plus c, of course, and this equals to ax plus ka squared plus by plus kb squared plus c. And what do we see here? Here is ax, by, and c. What is this? this is actually 0, because this is actually the point which lies on the line, and its functional value will be 0. So what remains is k times a squared plus k times b squared, and this equals to k times a squared plus b squared. Now, let's have a look back to the distance, because we often want to calculate the distance of a point to a line. And if we have an implicit formulation of the line, here is how it becomes very handy. So we already defined that this distance is k and times the square root of a squared plus b squared. But now we still have this k here, which is not very practical. So we can actually express this term here as a squared plus b squared divided by square root of a squared plus b squared. This is this term times k is this full term of this. However, observe that this is our functional value of the point. This is this part. So actually, we can just define our distance as functional value of the point xp and yp divided by square root of a squared plus b squared. And this way we will get the distance of the point from the line, even without knowing the projection and even without knowing the k. This can be very handy, and if we will normalize our values a and b and c by this term, 1 divided by square root of a squared plus b squared, then we will ensure that we will have a functional value which will be equal to the distance. So, as you know, we can change and multiply our implicit formulation by arbitrary term, and this will not change much for the function equals to 0, but this will change the scaling of the distance or the functional value outside the fxy equals to 0. And if we want to become true distance in the same units, then such a scalar multiplier of a and b and c would be then practical to use. After looking into the implicit formulation for lines, we can also have an implicit formulation for other functions, like for example for quadric curves. Here you can see a general formula for quadric curves with different terms associated with each version of variables or their combinations. One of such quadratic functions could be, for example, a function of an ellipse. We can see here that it looks similar to a function of a circle, meaning that we have here a function of a quadratic function of x at a distance from a certain center. And this point, however, is in each coordinate axis additionally weighted with the term a and b. So in case these two terms will be equal to each other, our ellipse will be in fact a circle. However, if these two terms will be unlike each other, then we will have an ellipse. In the image, you can see the role essentially of this of these two um, characteristics of the ellipse of A and B, and they are essentially scaling the ellipse in one or the other direction. The bigger is, for example, the A, the more it will be horizontally elongated, and the bigger will be the B, then the longer will be the elongation along the y-axis. This ellipse is, however, only an ellipse which is axis aligned. So if we would like to create an ellipse which is arbitrarily rotated, we would either need to have a different quadratic function formulation, or we would need to use some transformations of the axis aligned ellipse to be applied on the top of the original function. Let's move on from the 2D representation into a 3D representation in an implicit form. We can have exactly in the same way as we had xy equal fxy equals to 0 functions, we can just add one more component, the z component, into the formulation. In case of 3D, our points will be characterized by three coordinates, and these points will be evaluated whether or not they belong to the function under the value 0. And if they will, then they belong to a certain surface. As we described before, we use the gradient function to compute the normal of our particular implicit surface. So we can see here that the computation of the normal is simply partial derivatives along x, y, and z coordinate that form as the respective coordinates of the normal. Now, if we have a look at the plane, there we can see an interesting implicit surface formulation where we have our normal, which characterizes the plane by the fact that it is this normal is perpendicular to this plane. And then, however, such a plane can be placed anywhere in space, so we will need a characteristic of one point which belongs to this plane. And this will be the point A, which is our sort of a characteristic point for the plane. And this point A then can be used along with the normal vector for evaluating whether some other points lie or belong to the plane or not. And we are using here the dot product between the normal vector and the vectors AP spent between the points A, which belong to the plane, and the point P. If the dot product will be equal to 0, meaning that there is a 90-degree spent between the normal vector and the AP vector, this will mean that the point P belongs to the plane. If we would have 3 points and instead given, and we would like to compute which plane are they defining, we can proceed in the following way. We first define two vectors from these 3 points, a vector AB and a vector AC. Then we will perform a cross product of these two, which will generate us a vector which is perpendicular to the vector AB and perpendicular to the vector AC, which both belong to the plane. So this way we will define the normal vector. And after the normal vector is defined, then we simply follow the above formulation, where for any other point P, we can test whether the functional evaluation results into 0, meaning whether the points belong to that plane or not. The functional description of quadric surfaces can, in the implicit form, in the vector form, look very similar or even identical to the two-dimensional case. We can see it on the example of the sphere, where we see in the vector form that we simply evaluate the square difference between the points or the dot product between the vector PCN itself and the which will result in the square of its length and the square of the radius. And if these two distances will be even in a squared form or in the square root of that will be identical to each other, then this will mean that the point is on the surface of the sphere, and this functional evaluation will result into 0. Here we have an example again of an ellipsoid, which is again an axis-aligned ellipsoid, and it is defined in 3D. So now we no longer have an ellipse, but an ellipsoid surface. And we can see that the terms are very similar. We have one more scaling factor, C, which will be scaling the extents or the elongation of the ellipse in the z direction. Other than that, the formulation is analogous to the two-dimensional case. So far, we have been discussing the formulation of geometrical elements such as shapes and surfaces in their implicit form. And such a form had an advantage that besides the actual surface, we were able and we were having access to evaluate whether some points or objects are inside or outside and what is their distance from the surface of our object. But this is not the only representation, and a very popular representation is a parametric representation of these geometric entities, where we will, for each coordinate, we will define a particular element through functions corresponding to their individual coordinates, and these functions will share the same variable, the same parameter t, which will then be defined on a particular interval. So for example, if we have a line, we can define the parameter t on an interval from, for example, -infinity to infinity, and we will get an infinite line. We can define such a line by points which belongs to this line and their x and y coordinates. And for that we would need, as in the case here, we would need to define first 2 points. As in the graphics, we see point P0 and point P1. And their coordinates will be used first to define the vector P0, P1, which is one input for defining the line, and the other input is the starting point from which we define the line. So we anchor this vector somewhere in space, which is this part, which is the P0. And then if we are multiplying the vector with any value, we will define by that the line. Like for example, if the t parameter will go between will be equal to 0, then we will define by that, then this term will be 0, these two terms will be 0, and then we will be defining the point P0. In case the t will be having the value 1, what will be the result? X0 plus 1 times x1 minus x0 will be x0 minus x0 will result into x1. So between 0 and 1, we will have the result of x1 will correspond to the point P1. What will be the result if the t will be 0.5? Well, in such a case, we will go from the point P0 halfway towards the P1. So we will end up at this point. How about, can we enter other values of t? Of course, we can have a value of t also negative or higher than 1. And by this, we will be defining points on this line, on this entire line, not only on the line segment. This way, we, for example, define point with the parameter 1.5 or point P with the parameter -1. So this is a parametric representation, and we will be often using parametric representation for defining arrays in computer graphics. So the arrays will be defined this way, and then we will be computing intersection with objects in the scene. And if they are analytically defined, we can, for example, use their implicit representation into which we will put in the values from the parametric representation in order to find the intersections, or better to say, in order to find the parameter t values where these intersections with the object in the scene with the ray are happening. Another parametric curve definition can be defined for a circle, for example. So you can see here that the circle is defined as xc, yc, so each coordinate have some kind of a center. So this is a center of a particular circle. So here we have the center C, and then we have an r, which is the radius, times cosine phi angle, or for the y coordinate, the sine phi angle. And the phi goes from minus pi to pi. So if we draw it, then plus minus pi is here. We are going with this phi value from minus pi to pi, and with this we are parametrizing the circle. So let's imagine that the phi is equal to 0, for example. So if it is equal to 0, then we have cosine phi is 1, xc plus r will result in the, if this is the length r, will result into this position. So here we have the phi equals 0, and for the sine, so this is the 1, for the sine it will be 0, so that's the y-axis. On the y-axis we will be here. If we, for example, enter the pi half, so cosine for the pi half will be 0, but the sine pi half will be 1. So 0, 1, they will be here. So we can see that we are nicely finding points on this unit, on this circle. This is not a unit circle, this is a circle with a radius r. And the cosine and sine function are nicely parameterizing this for us. This is in some sense obvious because we know that if we are changing the angle, we can express it as a combination of cosine and sine values, which will be then the projections on the individual coordinate axes and their lengths. So this in a way makes it possible to see that these two formulas for each coordinate are nicely defining as a circle. How can we change such a representation, let's say, to an ellipse? It is easy. We can simply just use an different multiplier for the x and the y coordinates. So we do not have just one r here, but we have an a value for the x-axis and b value for the y-axis, which will be scaling us these radii. And again, it will just result into an axis-aligned ellipse, not in an arbitrary ellipse. Let's have a look at the third dimension, and we can see that we can create with such a circle. Here we have just a simple unit circle in a way, with the center point at the point 0. So there is no center point defined. So there is a 0 origin, so to say. And our z value is parameterized by the t. So from minus pi to pi, we will this way create, instead of staying on the same plane, we will basically extrude this circle into something like a spiral with exactly one revolution if the t will be parameterized from minus p to p. Let's continue having looking at the three-dimensional case. Here, often we in 3 dimensions are not only interested to look at lines in 3 dimensions, but actually in surfaces. And these surfaces we can parameterize with 2 parameters instead of just one. And these two can then define us, each of them defines us, if one will be fixed and the other one will be varying, then it creates us some kinds of isoline. But if both of them are varying, they will create us a surface. Such a parametric surfaces representation will therefore go from R2 to R3. The input will be 2 parameter values, and the output will be a corresponding point in 3D. Let's have a look at a parametric representation of a sphere. So this one is coming from the representation of a circle in 2D, but now we are extending the parametric representation into a sphere. Let's have a look at how it looks like. We can see that this is the parametric representation, and for X and Y, we can see that we have there already this circle representation, which we already see from the previous slide how it works. However, now we do not have the center point, so we have an assumption that the center point is at 0. But other than that, and this circle seems to be a unit circle. No, it's not a unit circle because there is an r radius. But it is furthermore scaled by another angle. So this is the second parameter. We have here one parameter is the angle phi, and another parameter is the angle theta. And this parameter is now scaling for us somehow we can see it if we just omit the z coordinate for a moment. We can see that it scaling us both x and y coordinate uniformly by some value based on the theta. So let's have a look at where the theta is defined. We can see theta is here on this drawing, and we see that it is an angle which is spanned between the point and the z-axis. Now, if a point will be on the z-axis, this theta will be 0, and if it will be laying in the xy plane, for example, it will have 90 degrees. Now, let's have a look at what happens when the angle has 90 degrees, meaning pi half. Well, in such a case, so if theta is pi half, then sine will be 1 and sine theta equals 1. This means that we will just draw in the xy plane a regular sphere, a circle, as we did it before. So, and what happens if we are now having, let's say, theta equals 0? So in such a case, if theta equals 0, then we will be having a scaling with 0. So this whole term will be 0. Now perhaps it's a good time to see what does the z-axis do. So we can see that, for example, we stay with the theta equals 0. If theta equals 0, then cosine of theta, which is in the z-axis here, is equal to 1. So r times 1 will be r. So while x and y will be 0 in such a case, if theta is 0, the z-axis will be of value r. So here we will have somewhere the point. And you can see how this nicely plays together, that we are with increasing z value through this through the cosine term, we will be decreasing the radius of our circle. So on each iso level of z value, the circle will be toward, increasingly it will be smaller above the xy plane, and the same holds for the below xy plane. So this way we can use two angles to parameterize a sphere. Sometimes it is interesting to look at how such a sphere parametrization can be converted into points in a space. So which points does it correspond to? And this is what we did now with this parametric representation, but sometimes we want to go the opposite way. We know the values and we would the XYZ, and we would like to know the theta or phi angle. So the theta we can simply compute in the following way. If we look at a radius, so maybe we have a point P now again on this drawing, which is this point, and we are now looking at how to get the theta. Well, from the right angle and cosine, we can find out that the theta will be equal to z value divided by, so this is the z value, and the theta is here, z divided by the hypotenuse. And what is the hypotenuse? That is essentially the r. But if we are not sure whether this point lies indeed on the sphere, or whether it's smaller or the radius or bigger, then in general the radius can be computed by squaring each coordinate of that point and making a square root of it. For the phi, so this way we will find out the cosine of the theta, and then applying the Arcus cosine, we can obtain the theta value. For the phi, we can actually find out the value easier just by using the Aten function, which we already mentioned before, where the phi is again the angle within the xy plane or within the horizontal plane, so to say. And there we can just take the y and x coordinate in order to find out what is the phi value using the L02 function. We have been talking about what is a derivative of an implicit representation. Now let's have a stop for a moment and let's think of what is a derivative for parametric surfaces. So if we have a parametric representation for just one parameter, like for a line, the derivative of it would be a tangent at that position along a line or curve. If we are interested in knowing what is a derivative for a surface, then we will have to resort to partial derivatives in such a way that we will keep one of these two parameters constant and vary the other one. And by that, we will essentially, if as we are varying it, we will create an isoparametric curve, so-called, where we can compute the derivative, and the derivative will be again a tangent to this isoparametric curve. So we will create one tangent. Then now if we will switch the roles of the two parameters, and one will be the one which is fixed and the other one will be varying, then we will create another isoparametric curve with respect to the other fixed parameter. And again, the derivative at that position will give us the tangent vector to this other isoparametric curve. These two tangent vectors will be actually forming the tangential plane at that particular surface location. So using the cross product, we can compute the normal at that position. So the derivative of parametric surfaces, meaning the partial derivatives, will be creating us two partial derivatives, which if we are creating a cross product out of this, we will get the normal vector at that position. The next topic is an very frequently used form for parametrization. And if we have a certain set of points, we would like to span a continuum between these points. And for that, we are using some form of interpolation. A simple form of interpolation is the linear interpolation. And if we have, for example, 2 points, and we would like to create a line between them, we can linearly interpolate from one point to another point. Like, for example, here, we have the point A and point B, and we would like to create a point P, which lies in between these two and is refers to a position with a certain value of the parameter t, which goes between 0 and 1. Such a parametrization can be also used in case of several points, and let's say we would like to create a continuous connection between these points. This can be seen in the formula in the previous slide, and we can see it also here. Let's imagine that we have a certain set of points, and these points are defined by their Cartesian coordinates. And maybe here we have the point x1, sorry, P1. Here we will have the point P2. Here will be the point P3. And perhaps here we will have the point P4. Now, how can we create a continuous line between those? Such a linear interpolation function helps us here, and we can create an interpolation based on in case of a linear interpolation, based on between which points which we know our our interpolated points, it lies. So for example, let's say that we would like to create point which is at the position x equals 3. So if x equals 3, this is between the point P1 and P2. So P1 has the coordinates 2, 1, and the P2 has the coordinates 4, 2. So if we will now put these values here, we will see that this will be the x coordinate of P2, this will be the P1, and the same holds here for the y coordinate. This is the P2, this will be the P1. And we can see here that for the x here, we do not know the y. That's the interpolated value we would like to find out. And we are continuously changing the x, and we are finding the y here for the purpose of interpolation. Now, for the position here, we know that we are having the x equals 3, and we would like to know what is the y value. So x equals 3 minus xi, which is in our case the x coordinate of P1, is 2. So 3 minus 2 is 1. And here, this value is 4 minus 2 is 2. So this value, for this case, will become t equals 1/2. And now we have some known y values. So I will be 1, yi plus 1 will be 2. So 2 minus 1 is 1, and 1 plus 1.5, no, sorry, 0.5 times 1. So 1 plus 0.5 will equal to 1.5. So x equals 3, y equals 1.5. So we can see that this formula allows us to interpolate the points, and we have gained a new point here, which is the point at the position 3, 1.5. We can recognize perhaps that previously we have been dealing with the parameter t. Here we didn't have the parameter t at the beginning, but it was a parameter t once we started to evaluate this fraction here of the axis, because we ended up with a t of 1/2 between these two known points. So, and we have seen that previously the linear interpolation was defined as 1 minus t plus, so of a plus t times b. And here we have just once t, and here we have a 2. Well, this is because we have also here the yi twice. You can see that it's here and here. If we will move this y to the other side, we will also be able to create this factor 1 minus t as well. So those two formulations are identical. The last topic which we will be discussing are an omnipresent representation in computer graphics of surfaces or their approximation through triangles. Triangles we often need to characterize with respect to a particular position within the triangle. Like, for example, if we have different coloring on the vertices, we would like to interpolate the color among these vertices smoothly. For this, we are using the so-called barycentric coordinates to, to perform this interpolation, and we will explain it in the following. We also might need to do it for example, interpolating not only the color, but also for texture coordinates. Those are typically defined on the vertices, and we will need to interpolate those texture coordinates over the entire area of the triangle. Barycentric coordinates, again, will be handy for this task. So what are these barycentric coordinates? Let's start with a simple example. We have 3 points defining as a triangle, A, B, and C. Now, let's define 2 vectors, the vector AB and the vector AC. As we have these 2 vectors, in 2 dimensions, they are spanning us essentially a certain coordinate system with which we can express any point in this plane. For example, if we have a look at the point P here, this point P can be expressed as a twice the vector AB plus 0.5 the vector AC as an offset, or scaled offsets from the point A. So now we can see that we have 2 pairs of multipliers. One is the one we can call beta, and one we can call gamma, which are used for scaling these vectors in order to define a position of a certain point within this coordinate system. Also, we can redefine this a little bit different. So you can see that in the definition of the AB and AC vectors, we can see that the A point is appearing there. So if we slightly reformulate this, we have this formulation where the A is multiplied by 1 minus beta minus gamma plus beta associated with B plus gamma associated with C. So, and for the purpose of some consistency, let's define that the 1 minus beta minus gamma is equal to some alpha. And for a triangle, we can then use this alpha, beta, and gamma coordinates so that we have a barycentric coordinates definition, so that this triplet forms the barycentric coordinates. So, and this way we will define how much of a certain color value will be weighted from a particular vertex. And for a vertex A, it will be the weight will be the alpha. For the vertex B, it will be the, or point, it will be the value of beta, and for the point C, it will be the value of gamma. So you can see here once again an parametric representation of the point P, or the representation of the point P through these vectors and the multipliers. And this way we can find out or solve simple linear system to find out beta and gamma. Now let's have a look at this representation once again. imagine that now one of these vectors is the, let's say, the vector AC will be the, so this is the vector AC, will be the defined through a through an implicit formula of a line, as we have it described here. Here it's the definition of a line AB, but let's start with let's define the AC. Now, if we would like to, depending on the definition of the weights or of the ABC values of the line. So here we again remember have the formula AX plus BY plus C equals 0. So this implicit formulation we can multiply by a certain factor K, and this will not change us the values on the line, but it will scale us the values for the distances. Now, what we would like to achieve is that in order to have a proper characterization of such an implicit line definition, we would like that this line will reach a value of 1 when we will be intersecting the point B with this line. So in this implicit representation for the function f(a)(c), we will simply put in, f(a)(c), the x, b, and y, b coordinates, and it will give us some value. The value will be equal to some constant, and then this value we will scale our function of the implicit line FAC by, or actually by its reciprocal, and through this we will make sure that the value of this function of this line at the position when it reaches B will be 1. And through this, we will achieve that our barycentric coordinates will be defined through these implicit line representations and can use them for calculating the barycentric coordinates at a particular position within the for any point between these 3 points defining the triangle. Here once again the FAC is described in a more lengthy form for completeness, and its normalization with the factor coming from the functional value at the point B. Triangles can be also parameterized by barycentric coordinates computing in other way, and namely through areas. So imagine that the area of a triangle which is spanned between the, let's say, the area of A. Area of A is this area. So a triangle which is spanned by the other points than A, C, B, and the point which we are looking for the barycentric coordinates of. So this is the point P, let's say, and the PBC area is the area of A. So PBC triangle, and the area of the entire triangle is the ABC triangle. This is analogous for the other beta and gamma coordinates of our barycentric parametrization. Now, it's obvious that the total area equals the sum of A and B and C. So if we are diminishing an area of AA, the areas of AB and AC will be growing. We can calculate an area in the formula involving a determinant here, where it is essentially computed from a parallelogram area and then divided by 2. So with this, we can also calculate the parametrization, and maybe you can see if we are now having a parametrization for a particular point at a particular value beta, this value along the line where the beta is equals 0.5, we will have many different points, and they will have overall, each unique point will have unique barycentric coordinates. But for the points along this line, at a certain distance from the line or line segment AC, the beta value will be the same as we defined it before. And this is achieved by the fact that the areas of the triangles will be the same as long as the tip of the triangle, the point P as I was calling it before, is on this line of beta equals 0.5. Their areas will be the same. Finally, we will have a look at the triangles in 3 dimensions. This is where we typically, our triangles will exist, forming our 3-dimensional scene. Now, here we can again compute the areas of the triangle, but as we have in 3 dimensions the cross product at hand, we can make the situation a little bit easier. We can calculate the area of a triangle by this cross product. We know that we will calculate the vector out of the cross product, and its magnitude is proportional to the area of the triangle. More specifically, it will be 1/2 of the magnitude of that magnitude of that vector will be the area of the triangle. Now, with a little bit of optimization, because of course, if we have a vector, we will need to first calculate its magnitude, which will involve a square root operation and squared operations, which are more costly. We can optimize it a little bit and calculate a fraction between 2 areas, the area of the smaller triangle, which is defined by the point, let's say, PBC, and the area of the entire triangle, which is defined by the cross product involving A, B, and C points and the respective vectors spent between these 3 points. So with a little bit of optimization, alpha is shown here, how we can calculate the barycentric coordinate of alpha for a triangle in 3 dimensions. And that is all from the math, which we will need to recap before we can start with the computer graphics topics. And I am looking forward to see you on the next lecture. Thank you very much. Bye-bye.